All right, today, guys, we're going to be going over lipids. So, lipids are a different type of macromolecule. Remember the four macromolecules. We went over carbohydrates so far. We're going to get to lipids with this section, and we're going to get to proteins, nucleic acids in the next couple sections. Lipids are the one that's kind of just different from all the rest. So, the big thing that you have to know about lipids is they're insoluble in water. That means they're hydrophobic. If you break those words down, remember, hydro means water. Phobic means the fear of. So anytime you put these in water, they're going to separate from the water and not be dissolved. So like perfect examples you can see down here are fats, oils, phospholipids, steroids, and waxes. Think about putting all of those in water. They don't all dissolve. Like if you put sugar in water, you put salt in water, it's going to dissolve very easily. When you put lipids in water, they're hydrophobic. So like fats, when you put fats in water, they're not going to dissolve. Oils, when you put oils in water, think about like putting vegetable oil in water. It's not going to dissolve. Phospholipids, steroids, waxes, they all react the same way. They don't dissolve in water. Now, the reason behind here, as you can see, it says hydrogens attached to carbon are nonpolar. Remember back when we talked in our chemistry chapter, like dissolves like. So remember that water is polar, so it's going to dissolve other polar molecules. Lipids are nonpolar, so they're not going to dissolve in that water. Here's why the lipids don't dissolve in water and they actually push away from the water. If you take a look on this left-hand side here, this is a water molecule. We have partial positive charges around the hydrogens and partial negative charges around the oxygen. Remember that this is because the electrons tend to hang around the oxygen just a little bit more, and that means that, again, the electrons are negative, so they're going to have this little partial negative charge. Around the hydrogens, they're going to hang around a little less, so it becomes a little bit more partial positive. You have these different charges of the water, which makes it polar. Most things in life are polar because there's always some partial negative and partial positive charges around the molecule. In a lot of lipids, we have these long carbon skeletons, these long carbon backbones, and they're going to have these nonpolar bonds. So whenever you see one of these long carbon chains, you can automatically think, okay, it's probably going to be a lipid, which means it's nonpolar, it's not going to dissolve in water. All right, the first major type of lipid that I want you to understand and to kind of go through here is triglycerides. Now, again, start breaking down the words. I've told you that from the first chapter. Start breaking down words. Tri. What does tri mean? It means three. Think trident. Glycerides. We're talking about a glycerol molecule. If you haven't heard about a glycerol molecule, it's okay. But understand there's going to be three parts of this glycerol molecule. So, but what we use triglycerides for is long-term energy storage. So when you eat a bunch of food, you obviously can't store that food and just have it in your stomach for a long amount of time. You want to store it in different molecules. So your stomach's going to break these molecules down, and they're going to reform them into things called triglycerides. When you eat too much, or you have you have too much of a high caloric or a diet, you create too many of these triglycerides, and too many of them get stored into fat cells, and you start gaining weight. So triglycerides are made up of a glycerol molecule and three fatty acids. If you look down here, this is that glycerol molecule. You can see the three carbon atoms, and there's these hydroxyl groups on the right-hand side. We talked about functional groups 2 sections ago. These hydroxyl molecules are going to come in handy when doing one type of reaction. Now, this is an organic molecule. Remember, organic molecules contain carbon and hydrogen and other elements, but as long as they have carbon, they are an organic molecule. So glycerol is going to form 3 bonds with fatty acids. Fatty acids are a long hydrocarbon chains. You can see here they end with a COOH, which is known as a carboxyl group. These carbon chains can be really not any length, but there's a various amounts of lengths for them. But as long as you have 3 of them attaching to these glycerol molecules, it's going to create a triglyceride. Now, I'm going to move on here. Here's that triglyceride molecule. You can see the glycerol molecule here and the 3 fatty acids. These 3 fatty acids are why it's called a triglyceride. Now, looking back here, you remember we have this H and OH group here. So we have OH and OH, but you have an H and an OH here. The reason why we only have an oxygen left, but what type of reaction this went through. So we have an OH over here, and we have an OH here, but we're only left with an oxygen. You lost 2 hydrogens and an oxygen. So that's forming water. This is a dehydration synthesis reaction. So whenever this attaches, again, that fatty acid that attaches to the glycerol, you're losing a water and you're going through a dehydration synthesis reaction. There's actually 3 of them that go on between one glycerol molecule. So two different types of fatty acids that we're going to talk about are saturated and unsaturated fatty acids. You may have read this, or you may have heard about this on like cereal boxes or any food box or container that you have. You might see saturated versus unsaturated fatty acids. The saturated fatty acids here, you can see, example here is butter, but they are long, straight-chained fatty acids. Take a look, this is a saturated fatty acid. The reason why it's saturated, there's no double bonds between the carbons. What a double bond does, if you look over here on the unsaturated, this takes away hydrogens. Okay, so you can see there's a little bit of a kink here between this carbon and this carbon. That forms because of this double bond. When you don't have any of those double bonds here in this long fatty acid chain, it's called a saturated fatty acid. Think about a sponge that's saturated. It's full of water. Same goes for this saturated fatty acid here. It's full of hydrogens. Whenever you have a double bond here, you're missing 2 hydrogens. So because it's missing 2 hydrogens and because it has that double bond, you're going to have a little bit of a kink here. So whenever you see a kink in a fatty acid, you know it's an unsaturated fatty acid. The example that I have here for unsaturated fatty acid is vegetable oil. Using unsaturated fatty acids is a little bit better for us when eating. Your body can break these down just a little bit better than the saturated fatty acids. So that's why we tend to try to cook more with saturated fatty acids than saturated fatty acids. We can see here are 3 examples of fatty acids. These first 2 are straight chain. They're saturated fatty acids. Every single carbon has at least 2 hydrogens with it. Here's that double bond. Here's that where that double bond is. You're missing 2 hydrogens. So you have a little bit of a kink in that fatty acid. All right, so phospholipids, they're very close to triglycerides. A lot of students will think, oh, triglycerides are one molecule and phospholipids are totally different. Not the case. If you look at the structure of a phospholipid, most of the time you're just going to see this large circle and 2 tails coming out of it. But when you actually dive deeper into the molecular structure, you're going to see 3 of the same structures you found in triglycerides. You're going to find that glycerol molecule and 2 fatty acids. So if you replace this phosphate group that phospholipids have with another fatty acid, it becomes a triglyceride. So these are very closely related structurally and like the structural formula as well to triglycerides. The only difference is one of these fatty acids is replaced with a phosphate group. Think phospholipid, phosphate groups. You're going to have 2 fatty acids and a phosphate group. Now, those phosphate groups are very polar. You can see here they have a lot of oxygen. I give a hint to all my students. Whenever you see oxygen in a molecule, you almost know it's polar. It's just because oxygen is very electronegative. It pulls on the electrons more. It's going to create a lot of different charges in that molecule. It makes it polar. So we see 4 oxygen atoms here. We know this is definitely going to be a polar molecule. Phospholipid heads are hydrophilic. Hydrophilic things like water, they pull on water. Hydrophobic, again, we have these tails here that are fatty acids. They're going to push away from water. So these phospholipids are going to be found in the membrane of a cell. You can see here we have this double membrane, and the tails are on the inside. The heads are on the outside. This is because, again, these heads are very polar. So they're going to be attracted to the water in the cytoplasm and attracted to the water outside the cell. The nonpolar tails that are fatty acids are going to be clustered in the middle. This creates a great barrier between the outside of the cell and the inside of the cell because of the phospholipids that are and their tails are nonpolar on the inside and their heads are on the outside and they're polar. Another type of lipid is known as steroids. These don't fall under the category where they're going to be composed of fatty acids. I know I told you in the beginning that all lipids have fatty acids. Again, lipids don't play by all the rules of like the other macromolecules do. For example, carbohydrates, they're long chains of sugars. So sugars are their monomers. In this case, steroids don't follow that rule. They're still considered lipids, even though they don't have fatty acids. I'm not going to get into the minor details, but just understand that these guys don't have fatty acids. They are made up of 4 carbon chains here. You can see there's one chain here, there's a ring here, there's a ring here, and there's a ring here. So whenever we see these 4 carbon rings, we instantly know it's a steroid. If you're taking anatomy, you're going to talk a lot about steroids when you get to the endocrine system. These have to do with a lot with cell communication. We also see these in the membrane of cells. They help with fluidity, but they also help with some communication. Now, this cholesterol here can be made into testosterone and estrogen. The reason being is because the estrogen and testosterone look very similarly to cholesterol. The reason why they're just a little bit different here is because they have different functional groups. Remember those functional groups we talked about at the beginning of this section? They're just different bundles of molecules that we see consistently throughout the molecular world. I think the next slide, maybe, yep, here you can see they look very similar. So we have estrogen and we have testosterone. They look very similar. And from a quick view, you might think they're the same molecule. But look, there's an extra carbon here, there's one less hydrogen here, and there's some double bonds that are moved around. It doesn't seem like a lot, like to really change that molecule, but remember, small changes can have great effects. So one of these steroids, really changes how a guy looks versus how a girl looks. Girls have more estrogen than testosterone. Guys tend to have more testosterone than estrogen. Last group of lipids that I want you to know about are waxes. These are very closely related to triglycerides. The only difference is instead of a glycerol molecule, you're going to replace it with an alcohol molecule. These alcohol molecules will bond to usually 2 fatty acids, and they create great waterproofing, like things they can waterproof boots with, waterproof really anything that you cover wax with. But if you think about it, when you add wax to water, it doesn't mix. It's because, again, these long fatty acid chains are very non-polar. Water's polar. They're not going to mix.